Alright, so welcome back to another videos, and for today's video we have our another double sum where we have our index is m is equal to 1 all the way up to infinity, and our second index n is equal to 1 to infinity of m squared n divided by 3 to the power m multiplied by n multiplied by 3 to the power m plus m times 3 to the power n. So we got two variables going on. Again, it's a double sum, so we're gonna have to take account of that. So let's get started. Let's actually focus our sequence inside. I'm actually going to define it as a function dealing with two variables. So I'm just gonna define this to be capital phi of m comma n, and that's equal to, so this is our m squared n, and then divided by 3m n 3m plus m3n. Okay, and then notice that I can actually factor out the m outside, and manipulating this for later will actually make things nice and smooth. So this will be let's see, so we have, let me write the denominator first. And so that's being multiplied. So, and also I can just factor out the 3m since it's a product on the denominators. So this is m3m. Okay, so that's as simple as we can get for now. So now let's say that I switch our parameters. So m is our first variable we substitute, and n is our second. So now if I were to define the second function, the same thing as before, but we switch our parameters, variables rather. So that means everything from m that was from before originally becomes n, and then everything from n that was before becomes m. So this means we have, let's see, so let me work with the denominator first, and then this is m3n plus n3 power m, and then let's see, and then we have our numerator, which is n squared m, and then we can do the same as before. I can just factor out. So this time I'm going to factor out an n, and then factor out the 1 over 3 to the power n. So this means we have n m, all this being divided by n divided by 3 to the n. Okay, nice. Now notice that if we take these and put it back into our double summation with preserving our index as well, m is equal to 1 to infinity and n is equal to 1 to infinity, we notice that if we take the double sums of these two functions, they are actually symmetric to each other, because notice that the numerator and denominator, they're both commutative under, numerator for multiplication, and then commutative under addition. Although the only thing that's changed is our index m is here and n is here, but they both share the same index, so they are in a sense they're actually equal. They're actually equal to the same. So when I say that these two are symmetric, they're actually equal to each other. So therefore we can conclude that when we take the double sums, so let me actually write this out. Double sum from infinity to m equals 1, and then n equals 1 of capital phi of mn. This is also equal to the double sum. Okay, yeah. So the double sum of capital phi with mn, m being our first parameter, n being our second parameter, is equal to the double sum of capital phi where n is our first parameter and m is our second parameter. Okay, so because these are equal to each other, how about next, what we can do now is we can let's actually add the two quantities together. So this means because they're equal to each other, and I'm going to stick with what we have originally. So mn is so this is 2 times the double sum mn And so that's actually equal to the addition, our addition of these two double sums here. So we have, just rewrite this again. Okay, cool. And they shared the same index, so really I can actually combine this in just one quantity of the double sum itself. Meaning I'll write it this way. So okay, cool. So now let's actually calculate the additions of these two functions here. So this means, okay, so I'll take our formula m squared n, and then divide by 3 to the power n, and then n3m plus m3 to the power n, and then we just add it here. So that means, let's see, m squared n. Okay, so now that we have these two additions, let's actually get a common denominator. So this means basically I just have to multiply 3n here, 3 to the power n, to both the numerator and denominator. And I'll put this under one fraction as well, instead of separating into partial sums. So this means denominators, this has to multiply 3n, and then this is 3m. So this is 3m, 3n multiplied by n, 3m plus m3n. Okay, and then just multiply 3n to here. Now I can actually factor out m times n from the numerator. So when I do that, so it's n, m, or mn, whichever, it's commutative. It's commutative under multiplication, so it doesn't matter which order goes. So this should be, so I factor out m, so this is m3n plus, and then factor out nm here, so this will be n3m, then divided by 3m, 3n of n times 3m plus m3n, and this is commutative under addition, so it doesn't matter which order goes first, but notice that both these terms cancel each other out, so we're actually left with n times m divided by 3 to the power m multiplied by 3 to the power n, and I can actually separate the products out, so we get m divided by 3m, then multiplied by n divided by 3 to the power n. I'm trying to think if I have space. I think I can just move to the next. So this is what we have. So this means our going back to what we originally have, 2 times the double sum. So that means 2 multiply double sum infinity m is equal to 1 of what our product was, m divided by 3m times n divided by 3 to the power n. And then now what I can do is I can actually separate the or move our our functions m over 3m to coincide with our series index from m is equal to 1 infinity, and then move our n divided by 3 to the power n to coincide with this summation index from n is equal to 1 to infinity, and then just multiply those products of the series together. So in other words, this is the same thing as m is equal to 1, so this is m divided by 3m, and then multiplied by the other summation, n is equal to 1 of n divided by 3 to the n. Okay, nice. So far so good. Now, because we said that these two functions equal to each other, so that means even with the indexes, they're going to equal to each other. So how about to make things easier, how about we we define a variable such that that variable is equal to both m and n. So let's say, let me write this in red actually, just so. So how about we let, yeah, right here's good. Let m equals r, which is equal to n. Underline that. So we'll define r. So what this means is we have 2 times this double series. One, then infinity, n is equal to 1 of our capital Phi. And so that's equal to, so we let r, so substitute r for m and n. And notice that it's quantity square. So I can actually just write this as in parentheses, infinity, r is equal to 1 of r divided by 3 to the r, and then that square. And now I can just divide that by 2. So this means this is just 1/2 multiplied by our sum square. Okay. So now all that's left we have to do is we need to calculate this summation inside. So let's recall a little definition. So you guys remember the geometric series. So the geometric series is defined as when you have, all right, yeah, the rest of this I'm gonna write in red. We have that if r is equal to the index 0 of, and I'll just call this x to the r, this is equal to 1 divided by 1 minus x, such that the absolute value of x is less than 1. Okay, so that means x is in the open interval between -1 to 1. So okay, we have that. So let's manipulate things a bit. So if we let r equals 0, so that means x to the 0 is just equal to 1. Okay, so we'll just let 1 and then plus, and then we can actually fix our index again. So that means this is the same series, but our index now starts at 1 at x to the r. And then let's see, and that's still equal to 1 divided by 1 minus x. So how about this time, let's actually take the derivative of both sides. So we have the derivative in respect to x of 1 plus summation r is equal to 1 of x to the r, and then set that equal to the derivative of d to the x of 1 divided by 1 minus x. Okay, cool. So that, now taking the derivative is fairly simple. So we know that the derivative of 1 is just 0, so I'm not even going to include the 0 term. And so we can use the power rule, so we can take the derivative of the inside and just leave the summation outside. So when you do the power rule, it's so r goes to the front and then subtract that by 1. So that means we have let's see, summation r is equal to 1 of r multiplied by x to the power of r minus 1, and then that's equal to the derivative of 1 divided by 1 minus x. You can literally just rewrite this in terms of the powers of the exponents. So this is the same thing as 1 minus x raised to the -1. So that's just simply -1 divided by 1 minus x, and then well, x squared minus 2, don't forget that, and then take the derivative of the inside. So 1 minus x derivative of that is -1. Both those negative terms cancel out, so we actually end up with a positive. So this means the derivative of 1 divided by 1 minus x is equal to 1 divided by 1 minus x squared, positive 1. Okay, nice. And let's actually manipulate the summation a bit. So when we're dealing with the exponent powers, x to the r minus 1 is is equal to the same as x to the power r multiplied by x negative 1. So this means I can write this as 1 of r to the r multiplied by x to the power r divided by x. But our summation is dependent on r, so I can treat 1 over x as a constant, and I'll just smooth that outside. So this is 1 over x, and then summation r is equal to 1 of r to the xr. And then now what I can do is I can actually just multiply the x. So that means we have x divided by 1 minus x squared. Okay, nice. So now we're getting somewhere. So suppose we let our x equal to let me write this here. X equals 1 over 3. Okay, so we have that. Now we can actually just substitute. So when I plug in x is equal to 1 over 3, r is equal to 1, then we have r, then 1, 3, r. That means 1 to the r is just 1, and then it's just 3 to the r. So this is, and we're getting somewhere since we're getting exactly what we want, which is r divided by 3 to the r, which is what we're trying to compute. And then we can just plug in 1 over 3 for our x value. So this is 1 over 3 divided by 1 minus 1 over 3 square. And so this is 1 over 3 divided by 1 minus 1 over 3 is 2 over 3. So that's square. And then this is 1 over 3 divided by 4 divided by 9. But it's division over division, so I'll just flip the reciprocal. So if I move over here, so this is 1 over 3. Let me write it this way. Write it as 1 over 3. Then multiply by, flip the reciprocal, so it's 9 divided by 4 equals to 9 over 12. We can reduce that fraction, and that would just become 3 over 4. Okay, so we have that 3 over 4 is equal to our summation, our summation of r divided by 3 to the power r. Okay, nice. So now we have that. Now let's actually substitute that back in. So that means, so we have 1/2. Yeah, I'll just put it here. We have 1/2, then multiply by 3 divided by 4 square. That's equal to 1/2 multiplied by 9 divided by 16. Multiply the two together, and this is as simple as it gets. 9 over 32. Like so. Nice. All right. Pretty cool double series, am I right?